This is the PD toolbox. Let me start again. So basically you type PD tool and you get a PD toolbox. Let me see if I can do this. It's a lot easier. Okay, and actually this appeared on this screen, so I can draw a ellipse over here, I can draw a rectangle over here, and I think I can join them. How do I join them? And I think I can say boundary. Yes, pooling operation. Where did you find it? PD show subdomain labels. Okay. Yeah, I'm sure you can, but like basically you can mesh this thing, right? You can mesh this, and you can, for example, you can export the mesh. Okay, the window also appeared over here. Okay, you can save the name of the variables. For example, P is the points, E is the edges, only the boundary edges. So I like to call it EB, and T are the triangles. And I say okay, and these appear on here. Okay, and I also have a tool of extracting all the internal edges from the triangles and points. So basically E is equal to extract edges, P and T, and that gives you all the internal edges. So we get 44 edges on the boundary and 245 edges, including the boundary and the internal. So for example, we can plot it in such a way that P is the points, and the two dimensions are x and y, right? And if you the E is actually 4 lines. The 4 lines corresponds to, so if you open extract edges, the 4 lines of E corresponds to the first 2 lines corresponds to the index of the points, and the third and fourth line corresponds to index of the neighboring triangles or cells. So if you just want to plot them, you can say P1 is equal to P of column and E1 column. So that gives you the position of the first point of each edge, and P2 is equal to P of column and E2 column. That gives you the second point of each edge, and you can plot them by plotting so let's say P1. So the first variable is always the x coordinate. P2 of 1 column, that's the, I need a semicolon on this one, and also the same thing over here but plotting the y-axis. The y-axis is 2 and 2. Oops, also appeared on this screen. Alright, so that's basically all the edges, right? Let me do axis equal. Okay, in finite volume scheme, you always need the interface normals, because we are always computing the dot product of the flux, which is a vector, with interface normal. Actually, we are always computing the flux dot normal times the size of the edge times the kind of the length of the edge, because it's a kind of a flux integral along the edge. So it's usually useful to compute the normal of each edge. For example, I can compute the normal as P2 actually the second, so the normal is actually, if you compute the edge as dx and dy, right? So if P2 minus P1 is dx and dy, the normal is minus dy and dx. So it's x and y are flipped over. So P1 is P1 the y-axis of P1 minus the y-axis of Px is the x-axis of the normal, and you get then you get P2 of x-axis minus P1 of x-axis being the y-axis of the normal. All right. So for example, if we plot the normals, we can do a hold down on the graph, and we can plot. Oh, actually, let's say the edge centers are equal to P1 plus P2 divided by 2. That's like the center of each edge. You can plot the normals as EC, so the x-axis of the cell center, and the x of the edge center, and the x of edge center, let's say plus 0.2 times the normal, and one column, right? So that's kind of give you a small vector pointing towards the normal direction, and then everything is the same except for it's the y-axis. I make it 2, 2, and 2. Where is my picture? Oh yeah, okay. Now you can see I basically plotted a little kind of a vector from the center of each cell pointing towards the normal direction. And these are the quantities you are going to be using in the finite volume scheme for unstructured mesh. Yes?
So we really define the normal vector as like maybe pointing outwards the elements, so how do we ensure that in this operation? Because it seems like this, the orientation is maybe kind of arbitrary, either point into the element or outward.
Yeah, very, very good point. So, so the normals are always pointing towards, let me see, the way I constructed this. The normals are P1 minus P2.
So where is in trigonometry? Anti-clockwise.
Yeah. I mean, this way it's rotating it by 90 degrees
counterclockwise, right? So basically, I'm taking the vector of P1 pointing to P2 and rotating it counterclockwise.
Yeah.
So
do we need to add a check, like compared to the other node? Like they should be pointing to a different direction.
Right. So you need the so when you compute the flux and determine should the flux be added to a cell to a volume average or subtracted from the volume average, you need to figure out is the normal pointing towards that cell or from that cell. So in this code, I think I already did it for you, because if you look at the code, I actually find which side the triangles are by computing the triangle center and take a look at computing the inner product of the distance from the triangle center to the edge and the edge normal. And I switch the endpoints to make sure like the first triangle is on the left of the edge. It's a good thing to do, so that like you don't have to do the check when you are accumulating the flux. All right. So the procedure is basically like this. When you are computing a finite volume schema on unstructured mesh, we can compute. So let's say we are using Goodenough scheme, right? Only first order. So we compute the flux in each cell. So that's the first step. The same thing as we did in one dimension. Okay. And then that is going to be a loop through all the cells. But the next step is going to be a loop through all the edges. The first loop through each cells is going to be a loop around 152 cells. But the second loop is going to be a loop around these 245 edges. For each edge, we look at the cell flux on both sides of the edge, and using Goodenough scheme to compute what is the flux on this particular edge. Okay, it is very important for finite volume scheme to be conservative in the sense that the edge flux seen from both cells should be exactly the same. So it's a good idea to compute the edge flux only once instead of computing it twice when you are looping through different cells. So it's a good idea to actually loop through the edges and compute the flux only once. Okay, so once you compute the flux on the edge, you can immediately add the flux to and subtract the flux from the two neighboring cells, and that is what makes a finite volume scheme to be conservative numerically, right? You compute the same flux, and you immediately add the flux to one side of the edge and subtract the same flux from the other side of the edge. So the total amount in every individual operation is conserved. All right, does that make sense? Okay, any questions?
Can you repeat what you just said?
Oh, okay. So after you calculate the cell fluxes, you go through all the edges, all the interfaces. On each interface, you compute the flux. You compute the flux, actually, you compute the flux dot with the normal times the length of the normal, right? Okay, that value is what you need to add to one side of the interface. And it is exactly the same value where you should subtract from the other side of the interface. So for every pair of addition subtraction, the total amount of conserved quantity in the whole mesh is conserved. So after you do all these operations for all these 245 edges, the total amount of stuff within the volume is conserved. Except for, of course, when the edge is on the boundary, right, where you only add or subtract from the interior side and there is nothing to add or subtract from the other side. Or is it helpful?